Okay, so number one, it was balanced forces. And so what did that mean about the net force? Joseph? It was 0. And in this case, what happened? Like, how did they move? They didn't. So they were at rest, right? And so how can we describe the velocity? 0. Cool. And what kind of equilibrium is this? Mechanical. It is mechanical. There's two kinds of mechanical equilibrium.
The one that this one is?
The one that this one is correct. Static. Remember, static means not moving, right? So these guys were not moving. They were at rest, right? All of these words are appropriate to describe that situation in number one.
That makes a lot of sense with one that's coming in.
Good. Tell me what you're thinking, Isaiah.
So when we had we had one person on one side and then two people on one side, and two of them were the same, but the other guy was small. And then you had him start, and then you took away the small guy. Then it was equilibrium, but that would be dynamic.
Yes, it's exactly what was happening here. Do you guys remember? Maybe we should watch the video real quick. Okay, so it accelerated and then it had this 50 newtons one side, 50 newtons the other side. It was balanced again, right? Does everybody agree that 50 newtons one side, 50 newtons the other side is balanced? Mm-hmm. Cool. So it was balanced again, which means that the net force was 0. But tell me what happened. It kept moving.
Because it had a greater initial velocity.
Okay, so it had a velocity that was not equal to 0, right? But it kept moving at a constant velocity, right? And what kind of equilibrium was that? Dynamic. Good job. Okay. Cool. So, how does this make sense in terms of Newton's second law? So what does Newton's second law say?
Force equals mass times acceleration.
I actually like to write it as acceleration is net force over mass. Mathematically, so you might want to be writing this down. Just saying. Like, you got the fill in the notes?
No.
So I like to say acceleration is net force over mass because even though mathematically it's the same as net force equals mass times acceleration, physics-wise, I think it's important to realize that it's the net force that causes the acceleration. Okay? So when you're saying, like, how can I figure out the acceleration of this object? I need to know the net force and then divide it by the mass, and then I get it. So it's a little bit different because when you write F equals ma, it kind of makes it feel like that acceleration determines the net force, and that's not what's really happening physics-wise. So even though we use math as a tool, it doesn't always do all the physics thinking for us. Okay? All right. So if A equals F net over m, and F net is 0, then what can we conclude?
That it's at rest.
Joseph?
That there's no acceleration.
That there's no acceleration. That's exactly right. So does that mean that it's at rest? No, it does not necessarily mean it's at rest. All it means is that if it had a speedometer, that needle would be stuck right there. It's not moving, right? So this velocity is not changing. All right, so things can have 0 acceleration either at rest or at a constant velocity. Okay. How do you feel about this equilibrium situation and how you saw that in the net force exploration? Seem good? Awesome. Okay. So the next thing I want to explore from that video, and let's watch that video one more time. To recording. In general, when you see the velocity and acceleration having the same sign, what do you know is true? Anna? It's speeding up, right? This is something that we've done before, right? Speeding up, and then down here is speeding up. And so when they're in opposite directions, what does that mean? It's slowing down. Okay. Cool. So now, my question to you, and I will let you think silently for a second, is how does this relate to the net force? So think silently, don't say it out loud. Okay. Who knows? How does any of this have to do with the net force? All right, the net force. Yes, Joseph.
If it's accelerating, it has a net force.
Yes. If it's
It doesn't.
okay, if it's accelerating, it has a net force. Newton's second law doesn't just say that A equals the net force over mass. It also says that they're in the same direction. Do you know that? Because acceleration and force are vectors. Yeah? Okay. So now, what do you think about this? If acceleration and net force are in the same direction, can we finish filling this out? I think so too. What do you think, Vanessa? What do you think that first box is going to be? A plus or a right? Yeah? If acceleration is in the same direction as the net force and acceleration is positive, this means to the right, remember?
Yeah.
Okay?
Oh, okay.
And so it's the, did you guys notice how I color coded the boxes?
Yeah, I was gonna say like
It's almost as if I wanted you to notice that those were related. Thanks. Right? So the directions are the same. And so this one's right, and this one's left. So that's just how the acceleration and net force match up. So I want you to sort of actually imagine this, and it's going to be kind of funny because I'm recording. And so I'm going to be walking away from the iPad. Oh, actually, I could walk with the iPad, but they're not going to have any idea what I'm actually doing right now. So I'm going to do this first line. I'm going to walk to the right and speed up, okay? As I'm doing that, I want you to think about the direction of my net force. What makes sense to you? Ready? I'm going to walk to the right and speed up. Which way is my net force?
Right.
It was also to the right. Oh, look, there it is. Right? All right. I'm going to do the next line. I'm going to walk to the right and slow down. Ready? Oh. Right? The net force was that way, wasn't it? Can you kind of see it, that it was kind of pushing me back? Right? And then I can walk to the left and speed up, and then the net force will be to the left. Sorry, I just did the last one, my bad. I was just so excited to run. Okay, I just did the last one, and then now walk to the right and slow down, or walk to the left and slow down. My net force is to the right. By the way, of course, I'm doing this backwards for your benefit, so I got myself a little confuzzled there. But how do you feel about this? Are you like building some intuition for what that means, okay, in terms of the net force and speeding up, slowing down? All right, so the last question on the net force exploration that you did was, what can we conclude? If the net force is in the same direction as the velocity, what's happening to the speed?
Say that again?
I'm reading this. If the net force is in the same direction as the velocity, oh, there's like a missing verb. My bad. If the net force in the same direction as velocity, the speed is, what do you think, everyone? Increasing. And if the net force in the opposite direction as velocity, the speed is decreasing. All right, how's that feeling? Is it okay? It makes more sense. Oh, that's like a teacher's dream, to actually say something that makes sense. Okay, so when you actually did the net force exploration, it said at the top sum of forces, right? And that was the net force, right? So the question is, how do you actually do it without it telling you? Okay, so what do you think that top is? Why do you think it's 0? They're both the same and what? They're in opposite directions. Because if I said that it was the sum of the forces, you're like, oh, it's 150 plus 150. Why isn't it 300?
Because it's 150 minus 150.
Good, because force is a vector, right? So if we think about it this way, that like this way is plus and this way is minus. Sorry, I didn't mean to make that like an underscore. And that way is minus. Then you're really thinking about it like this. It's 150 plus a negative 150, which you're like, wow, Mrs. Renner, that's a weird way of writing that. What?
That's exciting stuff.
It isn't exciting stuff, adding negative numbers. What's a kind of more natural way of doing that?
150 minus.
Yeah, 150 minus 150, right? But what I'm trying to show you is I really am adding up these two vectors. It's just that one of the vectors is negative, right?
Which one is negative?
That's a great question, Isaiah. That's your choice, actually. In general, you could say positives to the right is just generally what we do. And so if something's pointing to the left, then it's negative. But you can choose any which way, right?
Can you get it wrong?
Can you get it wrong? Yes, of course you can get it wrong.
No, but if you choose incorrectly. Or is it just when they're...
If on a test I say, assume that positive is to the right, then you need to go by that. If it's not determined for you, then you need to define it yourself. But it always needs to be defined. When in doubt, to the right is positive and up is positive if we're going up and down. That's generally the convention, but you can always redefine it if you want, and then you just stay consistent. Okay? All right, what's happening over here with the 50s?
It's the same thing.
Yeah, it's 50 newtons minus 50 newtons, 0 newtons. So I think that probably is reasonably intuitive, hopefully. Okay? What do you think about this next one?
Either 50 or negative 50.
Okay. Oh, I'm sorry. Just kidding. There you go. Hi. Okay. Force is a vector. So it's going to be really, really important when we give an answer for net force that we also include the direction. Okay? So Lola, you said 50 newtons. That is the magnitude. Do you want to tell me the direction? Right. Fantastic. So F net, and you can write 150 newtons minus 100 newtons. And so that's 50 newtons. And then we want to make sure that we write the word right. Okay? Now, that actual information is in there already. Do you know where? It's really plus, right? It's really, right, a positive 50 newtons. But we want to be really, really clear so that everybody knows that we know the direction. So we're going to be careful and write right or left, okay? But this is the magnitude. And that's the direction. You guys remember the word magnitude? Right? So vector, right? He commits crime with both direction and magnitude, right? And magnitudes just means size, right? And that number is always a positive number. So it's just telling you the size of it. It's like what's on your speedometer, okay? Although that's a speed. Here we're talking about a force. All right, let's do one more.
200 newtons left.
What is it?
200 newtons left.
It's 200 newtons left. Let's actually see what happens. What's that?
Or just negative 2.
Okay, so if we say negative 350 newtons plus 150 newtons, right? Why did I write negative 350 newtons?
Because you're just going in the left direction.
Right? Exactly. It's just the left, right? This means left, right? But then we can use it mathematically, right? And so that's negative 200 newtons. Okay, that negative 200 newtons, that negative means left, right? And that 200 newtons is the magnitude. So, if that positive is defined, is well defined, you can write as your answer negative 200 newtons. Or you could write 200 newtons left. Does that make sense? So, honestly, what you will find yourself doing is you'll look at it and you'll pick the bigger one and then subtract. And then whatever direction the bigger one was in wins, right? That's the direction. Does that make sense? I think intuitively people do pretty well with these, right? But it is important to remember that you need to make sure you're adding everything in this direction, everything in this direction, right? And then it's this minus this. Okay. Ava, was there a question?
No.
Oh, okay. I'm sorry. All right. How are you guys feeling about these net force calculations? Cool. You want to take it one step further? Yeah, you do.
Oh, I know, we're adding mass.
Aha. Here is a question. And it asks, what is the acceleration of this object? How in the world would we approach this? Anna, you have an idea? Okay. Isaiah?
It's 2 meters per second squared.
Interesting. How did you get that?
Because you subtract 10 and 4, you get 6. And then I guess you just multiply the newtons by the mass.
You multiplied it?
Well, yeah,
So I would feel more comfortable if we had some equations. Vanessa, you're going to hook us up with those?
You said before that A equals F net divided by N.
I sure did, because that is Newton's second law. Uh-huh. And then you said, well, I need to calculate F net, don't I? And there you're like, cool, that's 10 newtons minus 4 newtons. So it's 6 newtons to the right is the net force, yeah? Everybody's pretty happy with that? Then I can plug it in. And by the way, if you have a question like this on a test, I am going to expect to see the work done, right? And don't just give me the answer. Yeah? Okay. So we have 6 newtons to the right. And then how do we know the mass?
because it says it right there.
Did it say this is the mass?
Yeah.
Yes.
It totally didn't. You know what? You knew things. How do you, oh, you saw the units. Because of your incredible knowledge, okay. Because of your incredible knowledge of your table of friends, you're like, kilograms? That's a mass, right? So you knew that. That was internalized. That was gorgeous. So now you know that's 3 kilograms. So the number math, 6 divided by 3 is 2. And then you're like, newtons per kilogram. Do you remember that yesterday? Just kidding, not yesterday.
Yes.
The last time we said that newtons per kilogram was equal to what?
Newtons
Meters.
per kilogram?
Yep, was meters per second squared.
I switched them.
Okay. And am I done? Oh,
Yes.
I circled the thing, but I'm not done. What did I miss?
Nothing.
The direction.
The direction. Good job.
Well, it's positive, so it's to the right.
Okay.
Are we gonna have to write what direction it is?
Yes. And I will make it very clear to you. I will put a little spot that says direction so that you don't forget. Or I will say, like, make sure to include direction in your answer. So I will remind you, because that's easy to forget, right? Because you just saw me, like, almost forget.
Give me a test.
Okay. This is called a scaffold problem. Do you guys remember what this symbol means? Right? This just means F net equals 0. This thing is in equilibrium. So these are like painters' hanging out on this big board. And these vectors that are coming off of like these two painters and then the board, what are those? They're in newtons. So what do you think that's representing?
Wait.
Weight, good job. Weight's a force, right? It's the force due to gravity. And so you can see those newtons and you're like, ooh, that's the weight of that guy. And then the middle one's the weight of the board. And then over here we've got this 200 newtons up, oopsies, from the rope holding it up. And then the question is, what is the tension or the force in the other rope? So take a moment and try to figure it out. What's the strategy? What's the idea here?
Balance it.
Yeah?
Just balance.
You want to balance it. You want all of the forces down to equal all the forces up, right? Does that make sense?
Yeah.
Okay, what you got, Isaiah?
So it's 140 on one side, 120 on the other, so you subtract those two.
No. We're going to add up all the forces that are going down.
Okay, you do that too.
And then it's going to be equal to all the forces that are going up. Does that make sense?
How does that even?
So so look, this is on the left-hand side is 360, right?
160.
And so 200 plus question mark, right? So it's question mark is 160 newtons. Let me show you why, now that we have the answer. If I said that this was 160 newtons, and then I asked you what's the net force, what would you do?
It'd be 0.
Yes, that's the hope, right? Because it would be 200, here, let me get a different color so you can see. 200 plus 160, right, is pulling up.
That makes more sense.
And 140, 100, and 120 are pulling down. Yeah? And so then they would cancel. Yes, Joseph?
So when I was doing it, I wanted it to be balanced, so it just doesn't matter if it's balanced.
What do you mean balanced?
That side is pulling up harder than
Yeah.
this side.
So basically it's because the reason that side's pulling up harder, can you figure out why? Because he weighs more. Think about if,
But not 40 pounds.
it's not pounds, but
Well, 20.
so the way that actually do these problems
Yeah,
is
I
with
got
something,
180,
is,
not 0 to 60.
no, it should be 160. I don't know how you're getting 180. Here, I'm going to pause. All right, so the last kinds of problems I want to show you are proportionality problems. And I wonder if you remember the strategy that we use for this. So I will show you to you. The first step is you write down Newton's second law, but you leave some spaces in front of each of the factors. Okay, so that's the first step. So then we read and we say, if I multiply the force by 4, but keep the mass the same. So then we look at here and we say, I'm going to put some numbers in front of my net force and mass according to what it just told me to do. So what did it just tell me to do to the net force? Malia? Put a 4 in front, exactly. Right? Multiply the force by 4. That's what I just did.
Keep the mass.
Keep the mass the same means what number goes in front?
1.
A 1. The next step is I say, what are these numbers? It is 4 divided by 1. And then I put that over here, 4. I can circle it because that is my answer. And here are some other ways to say it. It is 4 times the acceleration. You can say times 4. you could say, ready? This gets fun. Increase by a factor of 4. Hey, Matthew, do you want to go stand? Okay. Increase by a factor of 4. Do you guys know what that word factor means? Lola? To multiply. Okay? Because if I say that something increases by 4, what am I talking about? No. If I say that something increases by 4, addition. I'm thinking about addition, right? If I say that something increases by a factor of 4, then I'm talking about multiplication. So it's really important to get your language right here. If you get freaked out by the language and it gets like too rough, then just, do this math up here, circle that, and call it a day, okay? However, some of the questions that you'll see will use this kind of language. And so I want to make sure to spend a little bit of time where you're listening about that, okay? All right, there's 3 more little problems on the next one. Okay, why don't you try that next one?